So everybody, nice to meet you. Thank you for joining. My name is Omid Vadati. I will be your host for today. Today we're going to talk about AWS EMR. This is a series of lectures, kind of a course-like environment. We're going to teach everything slowly and slowly using a methodology. We'll cover all the basics that you need to get started on AWS EMR. This is a rather technical session, but it's designed for beginners, meaning those who don't know the ecosystem, don't know how to work with Hadoop systems, and we're going to cover everything in the next session. You're more than welcome to open your microphones and ask questions and turn everything into a discussion. If it would be out of scope, then I'll let you know. But basically, every question is valid, and I'll be happy to dig into everything, essentially. So before we start, a little bit about the community, so it will be clear. We are a big data demystified community. It's a worldwide community with over 10,000 people in Israel. I'm originally from Israel. And we have groups in about 30 countries around the world, and we just consult about data and teach data in the community for free. There's no business agenda or business motivation except pure fun and the love of helping the community. What you can see here is the community website. Everything we talk is uploaded to this website and categorized according to subjects. So you're more than welcome to join us. As you can see, 39 groups in exactly 23 countries around the world, in the US, in Europe, and in Asia, and Australia. Today's session is about AWS EMR Demystified. You can join it in your country. It's the same content. Everybody worldwide are invited to the same session. So what's special about this event that we are going to cover everything from the beginning all the way to advanced level. And it's going to be fun. We're going to work together. You can ask me questions. If you want to do your homework, you can do homework. If you don't want to, it's also okay. And we should have fun together. So feel free to ask questions and I encourage a discussion about everything. So if you don't understand anything, this is the place to ask your questions. Okay, can you see my screen, just to be clear?
Yes.
Thank you. You're more than welcome to use the chat as well during the conversation. If you're too shy, you can engage with the other participants via the chat. It doesn't bother me. Just please preserve a respectful way of contacting people and talking to people, and everything is cool otherwise. So, okay, allow me to get started. I'm gonna start and talk as slowly as I can, try to dig deep into everything I speak, but feel free to stop me and ask everything. Okay, if it's too much, let me know. If you need to slow down, explain some jargon or expression you don't know or not familiar with, just let me know. I'm here to help. Okay, So, getting started. This session is about AWS EMR. This is part one. I'm hoping to do 4 sessions every 2 weeks, give or take, same hour. Those who can't make it for some reason for following sessions, the recording will be sent if you RSVP, yes, and then naturally everything will be uploaded to the website I showed you earlier. So let's start. So a little bit about the disclaimer. There's no financial motivation here. Simply love what I do. Although I'm a consultant and I consult a lot, this is just purely for fun. You're welcome to contact me either via email or via LinkedIn. Please don't use the Meta platform for messaging. It's terrible. The messages are delayed. So the easiest way would be to contact me via these two. I can even give you my personal phone number if you like to talk. And I love what I do. So just talk to me. I'll be honored to help you. About the community, it's an international group as we discussed. There's lots of groups, but the main one is Data Demystified to cover all things related to big data. A little bit about me. I worked a lot in the industry in the last 20 years in startups and media companies and some major enterprises you're probably familiar with from your country. Naturally, these are international brands with presence on a global scale. On a personal level, I have a third degree black belt in Taekwondo. I've been doing that for quite some time. And I like to skydiving and to lecture and help the community. Getting started. So 20 years ago, everything was quite simple in the past. There was a 3-tier application with operational databases and APIs and webs and a data warehouse, and everybody were quite happy. Going forward came big data technologies that made everything a lot more complicated because every week your infrastructure would break because it wasn't able to handle the amount of new data coming into your system. Then came the cloud, made everything a lot more complicated. The paradigms have shifted drastically. The methodologies have been drastically changing over time, making everything much more complicated for everybody. If I look left to right, just be advised I'm using a setup of 3 monitors, 1, 2, so I can track your chats on the left and on the right I have the lecture itself, and in front of me the camera so I can see all the participants, so I'll be able to know who is interacting with who. And then the third complexity that after the cloud came the invoice, meaning as architects, we need to not only treat big data and cloud challenges, and we also need to consider cost challenges. And it keeps going. The amount of technologies for big data keeps growing by the number. This is a rather old slide from 4 years ago. So my solution or approach for this is a simple cloud methodology. If you're not speaking, please mute yourself so it will be easy for the recording to hear my voice. Thank you. But if you want to say something, you can feel free to unmute yourself. It's a discussion if you have any questions. So the methodology was quite simple for me. I'm going to combine cloud methodologies and big data methodology and generate best practice. And this is my perspective for data engineering in today's complex big data challenges. Today's agenda, we are going to cover the basic jargon relevant for our conversation, an overview on technologies and features, and some useful blogs and summary. Okay, jargon. So lots of jargon needs to be explained in our course because there's lots of fine details that makes everything related to EMR highly complicated. If you are an experienced engineer, you'll be surprised the amount of considerations you need to take into account to make your code work flawlessly in production. So in the past, writing code was supposed to be enough to run perfectly in production. However, when you talk about analyzing data at scale, it becomes much more challenging. You need to consider your architecture, you need to consider cost, you need to consider how the volume of the data may affect your analysis and your ETL pipeline. So, Hadoop ecosystem was born lots of years ago. It was an open source project, and then it has evolved over the years to work in data center environments and cloud environments. Each major cloud vendor has its own distribution of Hadoop wrapped in a managed service setup. But today's discussion is going to focus mainly on AWS EMR service. So for today's jargon, you need to know EMR EC2, which is the managed service that allows you to manage servers, and S3, which is the managed service that allows you to manage storage at AWS. Transit clusters is a term that references clusters that are going up, doing a specific job, and going down. Meaning they don't save the data forever, they rely on external storage such as S3. Decoupling we are going to cover more detail. I have a slide for that. Compute and storage, you have to understand that compute is referencing CPU, and storage usually implies disks, either local or external. Resource management is simply a service or an application that allows you to manage, to orchestrate your workflow efficiently. Open source is simply open source code that is managed by Apache Foundation. DIY is a shortcut for do-it-yourself instead of using managed service. Autoscaling is a simple, simple methodology in the cloud that allows you to add more resources, go up and down according to your workload. Spot instances, we'll cover that later, not urgent for now. Disk-based versus memory-based. Some operations rely heavily on the amount. Disk-based operations versus memories. Some jobs require lots of disk space, some require lots of memory. And replication factor is the amount of times the data is replicated and saved on your local disk. Just notice there's 2 times autoscaling. Scale up and scale out, I have a slide about this later. So let's talk about the jargon. First, cloud versus data center. So the advantages of working in a cloud environment is an agile innovation becomes your primary concern. The idea behind using a cloud service that it's scalable, it's cheap to get started. You don't have to spend $10,000 to buy an expensive server. You simply pay by the hour for what you need and what you consume. It's easy to learn because it's highly documented and there's lots of communities around it, and there's lots of managed services that help you simplify everything by not relying on operational people to manage your infrastructure for you. PaaS is platform as a service. It usually implies that on top of a managed service such as ET2 and S3, there's usually another application, for example, Hadoop, that is wrapped as a managed service, and it becomes a massive platform. Data center, for example, not for example, in comparison, every change requires time. It's designed for peak scale. It's costly to get started, and it's very harder to learn because there's lots of practices you need to know, like disk and storage administration, like network administration. Network and security is non-trivial when we talk about old school methodologies. So in the end of the day, I've created a framework which is a simple series of questions that helps you understand what's the right technology for you. And in the end of the day, you need to understand which will be faster, which will be more cost effective for you, and which will be simple to maintain.
I have a question.
Please.
Wouldn't the cloud solutions also have better redundancy? Because obviously, if your data center goes down and you have it in-house, I mean, you're toast. As opposed to if you have a cloud infrastructure, you can always just move your stuff to a different data center somewhere else in the world.
You can do that in a data center as well. It depends how much you invest in your infrastructure. In theory, if in the past, before the cloud, there were large-scale applications in data centers with high availabilities and disaster recovery. So it's a matter of architecture, of design, and capex investment about your production. If it's a global scale, then naturally all the big players had disaster recovery data center in a different continent that has a replication of the data so they can switch in a matter of minutes. Does that answer your question, Dexter?
Yes.
Thank you. Thank you for your questions. Please feel free to ask questions, guys. This is a session for you guys. So scale up versus scale out. So the difference in the end of the day is really about taking one machine and adding more and more resources until it becomes massive server, or simply add the same type of server, just another one to the right, thus working with a cluster setup. Some applications are designed for scale up and some are designed for scale out. It's not a matter of better architecture, it's simply different architectures for different use cases. For example, scale up architecture usually implies a small cluster with active-passive methodology. It usually simple to maintain because you have less machines, simply increase the resources per machine. You can use that in the context of data for power queries on databases and large-scale drawing. But the cons is about parallelism because you have less machines. When you use scale-out architecture, you simply add more servers and each node can handle a fraction of the task when you're distributed on your cluster. The advantage is parallelism, but the disadvantage for power jobs such as power queries and joins, it becomes less efficient because the same job needs to use all different servers. Questions about this slide? Okay. So what's decoupled? Is this setup decoupled? You have a server and a disk, server and a disk, and server and a disk? Not really. It's a scale-out scenario because the disk is highly coupled with this machine. Sorry, the mouse keeps clicking for some reason. Is this decoupled? Yes, it's scale out because you're using external storage, so the disk is not coupled with the machine. So if the machine dies, you can launch a new one, just attach the storage and you're good to go. Is this architecture decoupled? Yes, it's totally decoupled because you have specific applications with clusters that handle the compute, for example, Hive and Spark, but they use the same storage, meaning one storage system that holds your data that can be used in different applications. Any questions about this? Okay. So another thing you should know that some systems may differ in the amount of in the billing system. One is fixed cost for 24/7 cluster, and one is pay as you go, meaning you pay for what you use. There's a question in the chat: does EMR provide scale up and scale out as well? Yes. However, you should know that EMR primarily was designed to be scale-out architecture. Imagine a cluster with 1,000 servers. Because when initially it was created, the idea was that in the end of the day, one machine is limited. It doesn't matter how many CPU on network card storage you put in one machine. In the end of the day, you're bounded to one machine. So a scale-out architecture will allow you to do 1,000 servers, even if each of them is massive, and then you can do really complicated use cases in big data. Another concept is to understand the difference between streaming and batch in the world of data. So batch processing is like a wave, a big wave in the ocean where a large chunk of data comes and you process it, and it comes in waves. Every 1 hour you get one chunk of data and you process it. Whereas streaming, it's like a sprinkler system where you get constant drops of water, which are data packets. And you need to process that in a low latency, short window, either it's minutes or seconds. Is this slide familiar for you, for anyone? Would anyone like to explain these 4 terms? Don't be shy. Okay. So this is a framework by, I believe, IBM. And the idea is that these four V's help design a big data architecture. The first one would be volume. The amount of data usually has an impact on your architecture. Velocity is the amount of new data you get per second, per day, per hour, per month. Velocity is the amount of problems you have in your data, and variety is the amount of the different types of data sources. Some, for example, structured data such as the Excel files, and unstructured data like music files and videos and pictures. In today's world, there are two major ways to analyze data. One is a SQL language, and the other one is using code. For example, PySpsark, Java, and Scala. The thing is that most people don't know when to use a code and when to use SQL. Essentially speaking, the reason why code was introduced as a way to analyze data, because there were lots of critical failures using SQL engines for big data, but it has evolved dramatically, meaning in today's world, you can use SQL to analyze as big as you want, as you like data sets, meaning even it's a petascale, you can use SQL for that. Furthermore, SQL has not been eradicated from the world, meaning there are lots of companies in the tech world using SQL to analyze data simply because it's easier to get started for analysts around the world, and lots of legacy companies still use SQL as a primary source of as a primary way to analyze data. Essentially, SQL can help you in today's world analyze structured and semi-structured data and join several tables. You want to be using code when your data is highly unstructured or you have logic that cannot be implemented via SQL. For example, looping over data sets again and again, and each time using the insight to revisit the data using the previous iterations inside. And you have some heavy duty parsing or highly nested values. Any questions about this slide? Okay.
No.
Yes, please. Okay. The thing to understand about Hadoop, when I started learning Hadoop about 10 years ago, I was lost in PDF papers, reading like 3,000 pages a week just to catch up with the world, to understand why is Hadoop important? What can you do with it? What problem does it solve? And I got lost in the amount of information there. So this is why I created a community, to create some sort of methodology that will demystify everything for people. So it will be simple to understand, simple to approach a use case, simple to select the technology to get started. In the end of the day, if we talk about Hadoop in the context of AWS, you have, or any Hadoop project, you can talk about this in the context of three major components. You have compute, storage, and resource management. The reason for that is because in the ecosystem of Hadoop, you have lots of technologies which are truly decoupled from each other that can do the same thing like any other solution, but they have a twist. They have something that they bring to the party that helps. For example, storage solutions in a Hadoop ecosystem simply handle how to save the data, how to read the data, how to write the data, how to compress the data, and so on and so forth. There are lots of storage solutions that have the same unified API to connect with all the compute and resource management technologies in the Hadoop ecosystem. This is simply one well-known example of compute, such as Spark, very well-known. It's part of the Hadoop ecosystem. And Yarn, also a very well-known Hadoop resource management application. In the end of the day, these are three different applications that are standalone and they communicate with each other over the network. Any questions about this slide?
I have a question, Mohan.
Please.
Can you hear me? Yeah.
Yes.
So, do we have any other compute resources which we can use for EMR in EMR?
Yes, there are
Except Apache
tons of them.
Spark?
Yes, there are lots of them. I will show them in the next slide, I think.
Okay, thank you.
For example, you can see there are lots of Hadoop storage technologies. For example, Hadoop file system, Apache Kudu, Amazon S3, Google Cloud Storage, Apache HBase. And per the previous question, lots of compute technologies. For example, Spark, Spark SQL, Solar, Presto, Tez, Hive, Omid. I kid you not, there's an open source project called Omid that integrates with the system with Apache Phoenix, Cloudera Impala, Hadoop MapReduce. Lots of technologies, and they all interact with the storage system in the same way. And they all interact with the resource management. Another resource management tool or application is called Apache Mesos. It's a very general framework that can be done and used for lots of use cases, but you should know that Hadoop Yarn is not the only one. It's the most common one, but you should know there are more. Does this answer your question, Shashista?
Yeah, thank you.
Okay, someone from the audience asked, what's the difference between Spark SQL and Spark? We're going to cover it later, but since you asked, I have no problem of answering that. Essentially, Spark is an API framework. It has the core API, which is Spark. And then on top of that, there are lots of other API. For example, Spark SQL, which allows simple SQL queries to be translated into Spark functions. And implementing a Spark job requires code. For example, PySpsark, which is Python API for Spark, or Scala or Java. And then you can use API framework of Spark core and you can write a Spark job. However, this is purely code. You can use Spark SQL, which is essentially translating, it's an API that translates simple SQL syntax, like select star from T, into Spark function. So if you're not familiar with Spark core, you can start with simple SQL and then work your way around to Spark core. Any questions about this slide? Okay.
Yes, I have a question, maybe a
Please.
general one. Yeah, it's a very general one. It's like when I talk or I'm in discussions around big data, some people are It's like I feel that some people treat Hadoop as something that is like something of the past, some technology of the past, as if now Spark is run, like the fashion now is to run Spark on Kubernetes rather than Hadoop. So I worked a lot with Hadoop and Spark, and I really don't know. I mean, not really regarding EMR, but what is the status of Hadoop as a technology? Is it being used as a legacy technology, or is it like a cutting edge technology today? I hope that I'm clear with the question.
The question is quite clear, and actually it's a perfectly good one, and I covered this one. And let's put it this way. As a consultant, I've been doing over 100 projects in the last 4 or 5 years, and I can say with some degree of certainty that about 80% of the use cases, there's no real need to implement Hadoop. Assuming in those 100 projects, I need to build everything from the ground up. There's no real justification to use Hadoop because it's a highly complicated piece of technology. But the beauty of working as a big data architect is, the way I see it at least, is to match a piece of technology to a business use case. So even if you need to implement something from the ground up and you need to choose a technology, it's non-trivial because there's lots of technology, not even a Hadoop. Not only Hadoop, there's lots of them. As I saw in that huge slide with many technologies, there's a couple of hundreds of technologies you can choose from. But in the end of the day, the answer to your question, it really is about the use case. You tell me your use case and I'll tell you if Hadoop is your answer or not. Generally speaking, you want to use Hadoop when you have a multi-petabyte scenario of data, even hundreds of terabyte worth of data, because you can do things with Hadoop which are very cost efficient in terms of infrastructure cost. But the downside is the learning curve and the management of such systems. Does this answer your question, Ronnie?
Yes, it does. I mean, I was well, actually, I worked on Cloudera systems. I was like, I mean, I was invited to develop for a customer that had like on-prem Cloudera, so that's what I had, and actually, I liked it very much. I felt very comfortable with Hadoop, with even with Hive, using you know, and working with Spark. It seemed like so matching so well together. And it was only in some meetups of other companies, some of them are using big data, that I started to see the questioning of Hadoop. Though personally, I mean, I worked also with Databricks, so when it was there up and running, or you know, either Databricks or EMR, it was up and running, it was great, or on-prem. I was just wondering about the general, but thanks. I think I understood your question. It's like to look at specific use case and
yes, and you should ask yourself also if you're in a cloud or data center environment, because managing multi-terabyte data platform in a data center is much harder to do if you don't have the right tools.
Right. Okay. Thank you.
You're most welcome. I see there are lots of interaction in the chat. Keep them coming. Feel free to engage with each other. So there are lots of other open source projects in the ecosystem of Hadoop that really integrate well. I can just throw some buzzwords into the air like Scoop, Zookeeper, Apache Pig, Elastic, and Strift, Zeppelin. But in the end of the day, it's all about your use case. You should know that there's lots of these Hadoop distributions around the world. I just put the major ones: Cloudera, Databricks, Amazon EMR, Google Dataproc, and Hortonworks. Today's session is about EMR, but the concept of using Hadoop is applicable to other distributions. Naturally, there are cosmetic, well, now even more than cosmetic changes between each distribution, but the majority principles and jargon should apply. So we're going to go over the technologies, because one of the things that happens when you start learning AWS EMR is they don't talk about the applications or the ecosystem that comes pre-installed as part of EMR service. And the AWS big data stack is massive. There's no real chance to master everything. So you need some sort of a map or an index that will help you navigate through this maze. So when they talk about marketing, the marketing team over Amazon talks about big data stack. So they take all the open source projects and put them under Amazon EMR. So immediately everything becomes much simpler to understand in terms of the data stack of AWS. Again, today's session will focus only on this part. So in the EMR ecosystem, as I said, has a long list of open source technology. We're going to cover just a fraction of them. It keeps changing. Every month or two, there's a new version, and they keep adding more and more open source projects. So it's really hard to keep track, but I will focus you to the main technologies that are relevant for you. Before we dive into technologies, let's talk a little bit about EMR technologies so the concept will be clear to understand. There are three types of nodes in your cluster. There's the master node, a core node, and a task node. EMR, essentially speaking, is very good for a transient cluster, a cluster that goes up and down, for example, every night. But you need to understand the different role of each node. A master node usually is one node. You can have more for high availability, but the master node holds all the GUI applications. For example, Hue that helps you write SQL queries, or Zeppelin to manage your flows, or Ganglia to monitor the health of your cluster. But essentially, the idea is to manage the jobs and the files where they are stored and which node can access what, when, and where, and why. So you should know that if something happens to the master node, the entire cluster is lost, meaning the entire compute can be thrown away and needs to be recreated. So if you're in a data center environment, you should have high availability for your master, but if you're in a cloud, it's less critical when you have a transient cluster because your storage is decoupled and saved over disk. And for example, S3, and you can simply replace your compute every day, every hour, every minute, and nothing will happen because your data is decoupled and saved on S3 in a specific bucket, usually in a package format. We're not going to go over too deeply about the storage formats today in today's session, but you should know there's lots of ways to save your data, and we're going to go over it hopefully in the next session. An example of the architecture implementation would be in EMR, would be using Yarn for resource management, Spark for the compute, where you have a master node, a core node, and a task node. So I illustrated the difference between the core node and task node so it will be easier to understand. You can ignore the master node for discussions. The important nodes are the core nodes and task nodes. The major difference between the two, is that the core node has a local disk, primarily used to write temporary files on HDFS, which is the local Hadoop file system. However, in cloud distributions, the local disk is highly irrelevant because you want to keep your data on S3 or any other cloud storage system. The reason for that, you want to be totally decoupled and you want to be transient. Forget a scenario where you have a 24/7 cluster, because this is one much harder to maintain a local Hadoop file system, and it's bounded to the amount of storage you have in the machine. However, any EMR cluster must have at least 2 core nodes. The rest can be task nodes. Task nodes are have the same functionality of the core node, except they have no disk, meaning they can offload compute jobs to other task nodes. But the assumption is that task node can read directly from S3, thus essentially fulfilling the same task as the core node. Any questions about this architecture or this slide?
Maybe a comment. I think it's a bit confusing what you are saying about task nodes, that they don't have disks, because if you have a Spark job with many shuffles, so you must have disks. Okay, so that's correct only for the cases where you can perform things in memory or without shuffles. If you do have shuffles, so your task nodes will have disks as well.
You are correct. Allow me to refine the slide. As I was speaking, I noticed there's a slight issue with what I'm saying. 1 second, I will fix this. Thank you for your comment. So what I meant, naturally, each server has a disk, because if you don't have a disk, you don't have an operating system, which is a problem. So what I meant, you don't have a local HDFS.
Yeah, HDFS even is not installed.
Thank you for your comment.
Sure.
I'm 1 second. Okay. Okay. Now are we in agreement, Grisha?
Yeah, sure. Thank you.
Thank you. So, essentially speaking, to fine-tune our conversation, you want to be using EMR prime Parquet file. There was a question in the chat about Parquet. Parquet is simply binary storage, which is columnar, to help you efficiently extract data when you save it. Meaning, imagine a scenario when you have 1 billion records in one table, you have 10 columns, and when you do select column 1 from T, you only take one fraction of your storage file, because this Parquet binary format allows you to efficiently skip the non-relevant data. Another question from the chat: when shall I use EMR over EC2 instances? every time you need Hadoop in AWS, you choose EMR. You don't want to manage Hadoop by yourself on EC2. This is very crazy. And I did that before, so I pretty much know what I'm talking about. Essentially speaking, you want to be using EMR for these three dominant use cases of compute: Hive, Spark, and Presto. We're going to cover each of them later, but the idea is that these technologies are good for data transformation, data modeling, and batch processing, and even for streaming. It depends on what you're using. So now we're going to go over the technologies one by one. Again, there's a possibility to install them in EMR. This is partly what I like about EMR. It has a lot of power and a lot of the flexibility you can use while working with EMR. Scoop is an open source technology that allows you to work with the databases and perform bidirectional ETL. It's usually unlikely that you get direct access to a source database, so we usually don't use that. Hive is a compute application that allows you to run SQL over HDFS or over S3. It uses behind the scene another compute engine. It could use Spark as a compute engine, which is rather confusing, but it's a possibility. Tez and MapReduce. You can connect via JDBC or ODBC, but it's not good when you need to shuffle data, and it's not designed for petascale scenarios. However, it has lots of surveys, and you can work with Parquet and regex to parse log files and do dynamic partitions, NISO override, and data transformation, lots of rich syntax for that, and you can convert to columnar. Essentially, this is an old slide of the Hive architecture, but in the end of the day, you have a metastore, you have a client, and you have an engine that allows you to process your data, whether it's on HDFS or S3. Moving to Presto. Presto has lots of flavors, one open source, one commercial, lots of connectors, but in the end of the day, it's SQL over Hadoop in memory. The downside of the architecture of working with in-memory databases is that it's not always good for joins with the two large tables, but in the end of the day, you can make everything work if you really know what you're doing. The downside naturally is that you're limited by memory, but you can overcome that. It's not fault tolerance like Hive. Hive is designed to fail because it's designed for long-lasting jobs. It's highly optimized for ad hoc queries. There's no insert override, which is a major bummer, no dynamic partitions, unless something changed recently, and has many connectors for Redshift and more. Apache Pig. It's essentially a distributed shell scripting, not very common, but it's used for people who don't know SQL and want to avoid heavy-duty code. Cube, kind of a favorite of mine. It's a simple GUI that allows you to write SQL queries on top of your sources and do straight up graphs out of it. Essentially a query editor. Spark, one of the most dominant use cases of EMR. It's in memory, usually 10 or 100 times faster than compared to Hive. Has a good optimizer, has a rich API. Following the question about Spark SQL, there's a Spark API. as you can see over here. And on top of that, you have Spark SQL, Spark Streaming, Spark ML, and graphics. And you have Spark R as well. Spark Streaming essentially lets you do near real-time processing. For example, 1 second latency. It's like working in very small batches. Has a specific API for that. It's usually not relevant for 90% of the use cases because sometimes analyzing data in 1 second latency becomes very complicated and generates very expensive infrastructure, and very little business use cases really need that. Having said that, there's a lot of use cases where streaming is highly justified. Spark ML, not a very common project, but you should know it exists, so you won't be confused. It's on top of Spark Core. There's lots of Spark flavors. You can install them from the ground up. Using a standalone version or with Yarn or with Mesos, doesn't really matter. Choose your flavor. Spark SQL has the benefits. It has the same syntax of Hive, which is very convenient. You can switch between technologies for different use cases. You can use Thrift to connect via JDBC. The trick is that it requires a non-trivial learning curve, usually 10 to 100 times faster than Hive because it's in memory. Works well with Zeppelin out of the box for you. It doesn't replace Hive. And in some extreme cases, Spark is not faster than Hive. It really depends on the type of use cases you have. The downside of Spark, you should know before you deep dive into Spark, it's not a trivial learning curve. It's very compute intensive. So if you mishandle your cluster, you may end up working very hard to achieve very little and pay lots of money in your monthly invoice. Performance gains of our legacy technology is not always guaranteed. Streaming processing is actually a batch on a very small window, so you need to understand the window that is required to your business use case. Different compiler behavior may occur on Hive and Spark SQL, so you should be minded to different behaviors of Hives and Spark SQL. Questions before I proceed? When shall I choose EMR over EC2 instances? Always, unless there's a margin issue on your production application, you don't want to use EC2. What does it mean to shuffle data? Essentially speaking, if we talk about this, I think I have a slide in the next one, in the next session. Let me pull it up now. 1 second. It will be easier to explain with the slide in front of me. So, essentially speaking, when you have a cluster of machines, the data is usually decoupled from the cluster, as we discussed over S3. But sometimes the data will be in one machine and it will be shuffling to other machines from the other machines in the cluster. This could be because someone loaded a local file into HDFS. Let's put the HDFS logo so it will be clear. Imagine this machine has the HDFS and it's this, you're joining two tables, one from there that the data resides on HDFS and one from S3. So essentially, this cluster will run the job and it will migrate the data from this machine to all other machines and pull the data from S3 and then redistribute the data as it sees fit on this cluster. Does this answer your question? Another question, is there a way to have autocomplete glue tables names inside Zeppelin? We're struggling with that for quite some time. Mickey, just contact me after the lecture or in the end of the session. Let's go over it if you like. In the moment, it's out of context. Okay. Moving back to our lecture. Downside of Spark and Zeppelin. Zeppelin. Zeppelin is kind of a cool project. It's a notebook. It's a web visualizer for data, query editor. It has a built-in Spark integration, so essentially you can launch EMR with Spark and Zeppelin and in minutes write your first query and get your visualization on top of your ETL job. It's very nice for interactive data analytics. It's easy, very easy to collaborate because your notebook is saved into S3. It uses SQL, Python, Bash, and you can combine technologies. It works on top of Spark SQL, Hive. It's inside EMR, and it uses in the background other open source technologies such as Shio for security and Livy for working with the distributed cluster from a remote client. Cut the bullshit, give me what I need. Sometimes there are lots of things that are confusing, contradicting, and never mind, regardless of how many blogs, PDFs, seminars, meetups you assess, there's no easy way to index everything. And you really get lost in the amount of information that is essentially being pushed to you. So over the years, I did some effort answering questions that are repeating from every session I do around data. And if the question is very long, if the answer to the question is very long, usually I write a blog about this so the rest of the community can benefit, because if one person asks that question, some other people asking that. So sometimes people ask me, when should you use EMR and when should you use EMR? Basically EMR versus Redshift. So the short answer would be, don't use Hadoop. If you don't know what you're using, why you need Hadoop, don't use Hadoop. As I mentioned earlier, for only 80% of the use cases, you don't need Hadoop. It's over engineering. But if you have to use Hadoop in the cloud or in the cloud, use EMR, use a managed service. Don't try to install Hadoop by yourself. This is madness. The amount of maintenance will kill you. Please, if you're not speaking, please mute yourself. Unmute you people. Thank you. It's not a punishment. Just, unmute yourself when you need to speak. So, as I mentioned before, the community website, the blog is here, and you can go over it and read that in depth. I kind of did it very dense and very straightforward. When to use Redshift, when to use EMR, and you can go over it yourself. But essentially speaking, I gave you the rule of thumb. Don't use Hadoop unless you know what you're doing. When should I use PySpsark, Impala, Presto? Also a common question because they're different compute and essentially they all allow you to do the same thing. Data transformation, data modeling. But there are differentiators. For example, Hive is used when you need a rich syntax to parse text and you have long-lasting jobs and you need to handle dynamic partitions. This becomes very easy using Hive. You can use Presto, Impala, and Spark SQL when you want to go in memory and really get a fast response to model your data. Questions about these two slides before I proceed? Okay. Now my headphone has, 1 second. Can you hear me?
Yes.
Thank you. Okay. Okay. What storage should I use? External storage such as S3, Hadoop storage format, and compression. On this question, I can, and I think I will, do a whole session and expand, but essentially, as a rule of thumb, you should always, in the cloud, you should always use S3, unless you have a really good reason to use local HDFS, and there are specific use cases where I would recommend to use HDFS, but in most times when you use EMR, you want to use transient cluster, and it makes sense to decouple your storage and save it on S3 so you can kill your cluster and when you don't need it and launch a new cluster and your data is preserved on S3 so you connect the two easily. As for Hadoop storage format, there are several Hadoop storage formats. There's Parquet, there's Orc, there's Avro, and each of which has even there's Iceberg and Delta Lake. Each of which has its own advantages and disadvantages, but essentially speaking, if you need a rule of thumb, go for Parquet because it's a columnar binary file type, which allows you in most cases get performance speed and the metadata, smart metadata, the schema to allow you to more efficiently create data skipping. In terms of compression, again, I can do a session about types of compression, and just to ease your mind, there's gzip, there's bzip, there's snappy. These are the most common ones. There are more, and sometimes you'll be surprised, but you don't want compression. There are specific use cases where you don't want to do that. But as a rule of thumb, go for, let's change the board so it will be easier to track what's the rule of thumb. Generally speaking, if you want to play it safe, you want to go on gzip. The reason why compression is a very important discussion is because imagine you have a scenario where you have 100 terabytes of data. We're talking about big data scenarios. This is why you want to use EMR and so on and so forth. And your storage is decoupled naturally. It falls upon you to understand what you're doing in the storage layer besides the storage compression. Second, allow me to close the door. Can you hear me?
Yes.
Thank you. So essentially, we talked about the 100 terabyte scenario worth of data, and using compression, you can reduce the storage size usually by 1-to-4 ratio. Meaning if the data is uncompressed, it's worth 100 terabytes in memory. But when you save it to S3 using compression, you can save only 25 terabytes, which is a huge difference in your invoice. It's about 75% cost reduction. Putting cost aside for a second, it also has performance impacts, meaning reading 100 terabyte uncompressed will usually take 4 times more than reading compressed file. The penalty for using compression is compression time and decompression time. Usually you want to be paying this penalty in compute to compress and decompress the data because you don't want to pay the difference between 1 petabyte compressed storage and uncompressed storage is about $7,000 a month, simply because you failed to choose compression. And the difference in performance would be 1 to 100 maybe. You may even not finish because you failed to use it correctly or failed to maintain your cluster, because if you fail to use compression, you fail to configure your cluster and pay attention to detail. So essentially, if you want to play it safe, as discussed, use S3, packet, binary file and gzip compression, and you probably hit the spot in 80% of your use cases.
What about the file size? Do you have a recommendation?
Yes, there are recommendations, but I don't want to give a rule of thumb except the following. Small files have a penalty. 2 large files have a penalty.
Yeah, but that's the question. So do you have something that you would recommend?
As a rule of thumb, no less than 128 megabytes. But I say that very, very carefully because each partition may have lots of files or low amount of files. So I play with the file size to minimize the amount of files per partition, and that should give the most benefit in terms of partition. But it varies from each use case to each use case. This is why you don't usually write this tip. It's a matter of trial and error.
Yeah.
Another common question is usually around, what should I do? What should I use? Should I choose SQL? Should I use Scala? Should I use PySpsark? So essentially, you can use SQL in 80% of your use cases. However, in some use cases, there are two benefits for using code. One, sometimes code is the only way to solve your business logic. And the benefits of using code like Scala is performance-wise, because as we mentioned earlier, Spark SQL uses Spark Core, which is written in Scala. So essentially, you're paying the penalty of migrating from Spark SQL API to Spark Core. So there is a difference in terms of performance. Question from the audience. Which part from EMR is responsible to uncompress the compressed file? The compute. For example, Spark. When you create a table, you mention which compression type is being used, and then the compute knows how to compress and decompress. So it becomes part of the compute's responsibility to compress and decompress, but you need to be able to state it explicitly. Is this slide clear? Any question about this slide? Okay, summary. I usually take this first session and slow down and even make it shorter than usual, but the following session will be as long as needed. The underlying assumption is that this baseline introduction is overwhelming, and whoever comes to the next 2 to 3 sessions really wants to go deeper and has done homework and has reviewed this session and is fluent with the jargon relevant for our future discussion, because there's lots of more technical, complex technologies and methodologies we need to go over with. But for today's session, we want to go over what we discussed, and I want to introduce you my framework and my approach to how I see things. As an architect, as a big data architect, in the end of the day, my job is to ensure all 3 vertices of this triangle are met. Faster, cheaper, simpler is the way I look at things. Is your architecture fast enough? Is your architecture cost effective? Is your architecture simple to maintain? The thing is, you should know that it's not always possible to achieve 3 out of 3. If you achieve 2 out of 3, it's usually good enough, because sometimes you can't achieve all 3. But as a rule of thumb, if you only achieve 1 out of 3, then you're doing something wrong. Question that we can turn into a discussion just to test your understanding of today's session. What do you think, in your eyes, will make EMR faster? Please open your mics and let's talk.
Maybe more sources, like more computing resources.
Yes, what type of compute?
What do you mean by type?
We have 3 types of nodes.
So we have to have worker codes, for instance, because we can also have some master nodes, but especially we need worker nodes, as I understand.
Yes, And
more master node is more for availability, as I understand.
yes, exactly. So in EMR jargon, your worker nodes are co-nodes and task co-nodes. Task nodes, sorry. And following Grisha's comments, I need to fix this slide. It's a picture, but essentially the co-nodes have HDFS and task node have no HDFS. So if you want to make your EMR faster, you simply need to add more calls or more tasks. Great. What will make your EMR cheaper or more cost effective?
Spot instances.
Spot instances is one way to discuss, but we mentioned some other ways to reduce costs.
Maybe
Auto scaling.
Auto scaling is one way. What else?
maybe using some transient clusters or
Transit clusters is another way. Indeed. What else?
You can also use reserved instance.
Sorry, what?
You can also use reserved instances for that. So
Yes.
basically reserve, yes.
Reserved instances are another way. Yes. What else? The answer is in this slide.
Residing the data on S3.
Sorry?
Residing the data on S3.
I know. Compress the data because it would have less volume.
Yes, all of you are correct. One should check out the differences between S3 and local HDFS. You can argue both ways. There are different storage tiers with different level of availabilities that have different prices. But this is not something you want to reduce costs here. You want to use S3, put your data there, even if it's more expensive than HDFS, to have transit cluster. This would be way more cheaper to use than local FDFS on 24/7. But the most dominant one would be using the right format and the right compression. Because if you use a different format, you will have different performance. Different performance will impact running time. Running time will affect billing. Is this clear? Just to give you an idea of cost reduction, that could be up to 90%, 90% in your billing difference. What would make your EMR simpler? Question, but it's a relatively straightforward answer. Just simply use a managed service of EMR. Don't try to install Hadoop by yourself. And try to use the dominant technologies like Spark and not the ones who are less common. So to sum up, my perspective on data engineering, that's all about the framework or faster, cheaper, simpler. Everything should be as simple as possible, but no simpler. And I created homework for you. I created this tutorial for absolute beginners to create a EMR cluster. Don't forget to kill it. naturally, this blog is on our community website. It's a step-by-step introduction with it's an introduction and step-by-step wizard to help you go through the wizard of creating EMR. It explains briefly every aspect of each selection. And we are going to go over other aspects of your selections in the next session. For example, in network and security, tips and tricks to reduce costs. And basically, I want you to be able to go over this blog, generate your first cluster, try to ask yourself questions because it's rather overwhelming to do it yourself the first time. So I try to make it as simple as I can. Once you do that, you should be able to understand the benefits of the next session, because in the end of the day, mastering EMR is about mastering your jargon, your architecture, understanding what this means before you do something will have greater benefits for you in terms of your architecture, in terms of cost, in terms of performance, which are all the major pain points of becoming of launching a successful project in big data. Should you have any questions about this exercise, you can contact me via email or via the community. You can enjoy the website for other contents. Please feel free to check out our YouTube channel for all the past meetups and subscribe if you like the content. This will help me spread the message a little bit more. And you can stay in touch. These are useful links and channels on YouTube, and that's essentially it. Questions before we wrap it up for today?
Okay, I have a quick question, or maybe not quick. Have you faced this problem where when you are scaling out, at some point the execution time gets higher instead of, it becomes less performant?
Yes.
After scaling out?
Yes, I have. What is the question around it?
Which threshold? Is there like some kind of threshold where you actually lose performance after scaling out?
In theory, no. I'll give you a rule of thumb. It's like eating candy. You can enjoy candy every once in a while, but if you eat too much candy, it becomes a problem because you need to go to the dentist to fix your teeth. So in Hadoop, it's all a matter of balance. You need to balance between everything. So you have a set of configurations basically to tune every pips in your architecture, in your flow. But the thing is, it really varies and changes from each use case and each job you run. So to try to answer your question, what I would do, to answer your question more friendly, I would analyze the type of jobs you have, run that specific job that is causing problems on a separate transit cluster, open Ganglia, and monitor the behavior of the job over the cluster on specific machines to understand what is happening. Are all the machines being used? Is the network spiking? Is the CPU spiking? Is the memory spiking? What essentially the behavior of your job? That should give you some clarity regarding what's happening. That's one way to look at it. The second would be to go over specific configurations you did in the EMR and specific configuration. I assume you use Spark, so a specific configuration in your Spark. Does this answer your question?
Yep, thanks.
You're welcome. Any more questions?
Yeah, some hot technologies now, Iceberg and Kubernetes. So do you have any experience with trying running EMR on Kubernetes and storage is Iceberg?
Yes. I have experience. Iceberg is quite nice when you want to achieve two things. One, schema evolution. We'll hopefully review that in later on sessions, but since you ask. So it's a nice thing, nice storage format to test, and it allows you to update the schema, or, to update and delete your data, which is also very nice and very challenging to do on standard Parquet storage system, because you need to manage the storage, which is decoupled, separate from compute.
Yeah, I mean, I know the technology. The question more about if you have, real world experience, like, can you compare it, for example, for like Parquet, we all know that it's great and solid technology. Iceberg, people use it, but like I understand that you have a lot of experience with Parquet, for example, or other formats, but
Yeah,
did you try actually,
yes.
for example, migrate to Iceberg and how it works? Mm-hmm.
I tried all the different storage type I presented. All of them bring specific advantages in specific use cases.
So, for example, would you suggest for someone who have a lot of data, let's say in Parquet, to move to Iceberg?
Do you suffer from a schema evolution scenario?
I have, in-house solutions for that.
Then don't.
Okay, so because the claim is that you have, better performance and stuff like that as well.
Then you need to benchmark and test it.
Yeah, exactly. The question was if you experience.
I have real world experience, but it really changes from each use cases. I don't immediately jump to Delta Lake or Iceberg.
Mm-hmm. Okay.
Because you need to balance the complexity of your deployment with the use case. How many data engineers you have with the team? How many data you have? What the amount of change? What are the amount of delete and updates you have? How many schema changes you have on average in a month? So on and so forth. Because in the end of the day, every data engineer should be able to handle schema evolution every now and then. So why bother with over engineering?
Mm-hmm. And Kubernetes?
Kubernetes. As a rule of thumb, there's no real benefit from my experience for using Kubernetes. The reason for using Kubernetes would be several reasons for that. One is to standardize your deployment, meaning you want your entire production stack to work on Kubernetes. This is one reason. And the second would be portability, meaning you want to be able to deploy your application on different clouds. So you need to have a standard stack of Kubernetes. This is not trivially achieved, but it's an architectural consideration that is relevant in multi-cloud scenarios or hybrid cloud scenarios. The third reason would be to achieve cost reduction. Meaning when you use a standard EMI deployment, each machine has a standard operating system which has an overhead. We're going to cover that in the second session. And when you have specific cost issues and you want to do cost reduction optimization on very large scale, sometimes reducing the overhead of the operating system by switching to Kubernetes and saving about 5% on your compute is worth your time. In most cases, I deal with, as a consultant, this is really redundant, overcomplicated. It requires a lot of technical expertise from your data engineer. So I won't use that. What you want to be you asking, if I may, is regarding EMR serverless.
Yeah, also.
We did some benchmark unofficially for a customer. In the end of the day, we did not find any benefit of using EMR serverless, as painful as it is to say. Perhaps because we didn't use it correctly, but we invested about a week to benchmark it in different scenarios, and the cost benefit ratio simply did not give you anything. It did not run faster, it did not save you cost, and it did not save maintenance. So if you ask me, when you are in a scenario where EMR is essential part of your architecture, the complexity is high enough and the amount of details you need to fine tune is so high, you want to remove other things you need to configure, tune, maintain, and focus only on your data ATL job. So someone is asking, how is there no cost benefit if you don't need the resources up all the time? For example, user queries. Well, in the end of the day, it's a matter of use case. But what you are suggesting is where a scenario where there's no servers up and running, and you have analysts running some queries. So every hour they send one query and you trigger serverless. Here's the thing you don't know about EMR serverless. You still wait for the EMR to bootstrap. So I wouldn't use EMR serverless for ad hoc querying. I would use 9 to 5 EMR cluster with auto scaling. That proved for me more sensible solution, very easy to maintain because it boots up at 9, saves the 5 minutes bootstrap time, and it's you can keep it very small with the minimum amount of machines. And once someone sends the query, immediately auto scale, use task to auto scale very, very fast. Scaling with task nodes is fast, so in the end of the day, it balances maintenance and cost and responsiveness and parallelism. So it's not trivial to ask that.
By the way, auto scaling, is it supposed to also scale down? Because we did some benchmark and we saw it scaling up, but it wasn't, the size wasn't reduced after the load passed. Is it supposed to also to scale down after that?
Yes, it's supposed to scale down and it works perfectly. There's something wrong with your policy then.
Okay.
Okay, you need to test what's wrong there, but it usually works too good.
Okay. So you see it like goes up and down and just is the magic?
It's not magic. You need to work for that. Need to make the magic happen. You need to test the scenario and to understand when is it good to use auto scaling, in which scenarios it will be better to auto scale, because when you auto scale during a job, the side effects are not what you think always. So you need to be smart about what you're doing. And going back to the previous question about serverless, if you need an ad hoc query technology, use Athena, AWS Athena for that. Don't use EMR for ad hoc querying. It makes more sense. Any other questions? Okay. Guys, thank you very much for showing up, asking questions, participating. The next session would be in 2 weeks, I believe. It will be EMR and Demystified Part 2. It's on November 15th. I will share the slides in an email for those who RSVP'd. Yes. Please feel free to contact me, preferably via email or LinkedIn, not via Meetup. And I'll be happy to answer any follow-up question you may have. And be sure to check out the next session to go over network security and cost reduction practices. Okay, guys, thank you very much. I bid you good day, good night, good morning, depends on where you are in the world. That's it. Bye-bye.